Sounds like the mic is on. Great. Hi, I'm Benjamin Quiring. This is joint work with my advisor, David Van Horn. We're at the University of Maryland. And this is Deriving with Derivatives, Optimizing Incremental Fixpoints for Higher Order Flow Analysis. So what I want to do in this talk is go over an example kind of program analysis, and then how we might derive an efficient implementation of that. So for some background on program analysis, what we want to do is understand the behaviors of programs. For a small step semantics, what that looks like is like the traces of the programs, where you step between the states. But traces are infinite and uncomputable, so we have to settle for some kind of finite abstraction. And a really common choice is to associate with each of our actual program states some kind of abstract state, like that maps the number 2 to the number even instead. And the program analysis is sort of this collection of all reachable abstract states, and that's sort of an overapproximation of all possible behaviors of the program. So in order to compute the set of all reachable abstract states, what we have to do is a little fixed point, because it's essentially a graph traversal. So we have a set of seen states, sigma, and at each iteration, we're going to find the successors of all the states, and then we're going to add those back into the pile. So that looks like this. And the inefficiency of that is that you're taking the successors of these nodes, and you're taking it over and over and over, and you're always computing the successors of the same nodes. So this isn't super efficient. But since this is a graph traversal, we know how to do an efficient implementation, which is like use a workset. So when we use a workset, we remove a single state out of it each time, and we just explore one state at a time, and we make sure that we never reprocess the nodes. So we're going to make our program analysis a little bit more complicated now, and we're going to look inside of it and see what happens. So a state consists of like a program location and an environment and a store. So I'm going to use kind of a CPS kind of language where there's only function calls, so f applied to argument. This environment maps variables to addresses, and addresses are kind of this finite set of thing that determines the precision of your analysis. And finite means your states are going to be finite. And the store then maps the addresses to values. So to look up a variable, you go environment composed with store. And then values are sets of closures, which represents kind of like this closure could be assigned to this variable. The transition function distributes over the set of states and finds the successors of each state via this inner piece. To find the successor of a state, you look up the value of the function and the argument with this helper function e. Then for each possible closure that's in that value for the function, we step into the body of the closure, update the environment, and update the store appropriately. And we have to come up with a new address, but that's not the point of this talk, so I'm going to put ... So the problem with this program analysis is that you're going to get a whole bunch of similar states that only differ in the store, basically because of a program analysis that runs longer will have a bigger store, even if it's at the same location. And the solution to this complexity blow-up is store widening, where we're going to extract the stores and have a single global store and sort of what we call a set of configurations, which are like states without the stores. So when we do this transformation, we have to update the successor function. So now we're going to take in a pair of things, a set of configurations and the store, and we're going to distribute over the set of configurations. When we return, we're going to return not singleton successor states, but a pair of a new configuration and a new store. And then since the store is global, we no longer have to return the whole store, but just the update to it. So how do we get an efficient implementation of this analysis? So we can take the spec fixed point that we had before and just replace everything with a tuple. And this works out just fine as a spec. But to generate an efficient solution, it's not so easy. It might not be so easy to create that sort of really efficient workset implementation that we wanted. So in the literature, what it says is you can like adapt this set of states approach where you kind of revisit the nodes again in the graph if the store has updated. And so we're going to try to do something better and sort of derive that from the spec of the fixed point. So why can we hope to do better? It's because in general, these fixed points are dealing with lattices and monotone functions. So we have this v, and we have this f. And f is a monotone function, which means if you give it a bigger input, you're going to get a bigger output back. Again, this is inefficient, because as you give it bigger and bigger inputs, you're redoing work. So the idea of how to get an efficient implementation is to exploit this monotonicity. So if we take f and we give it a bigger input, then the result should be the old input joined with some new extra piece. And so this extra piece is measuring the change in f with respect to its input x, and so that's a derivative. So it turns out we can make an incremental fixed point with this derivative. So before we were joining this result of f in with v every time, and now we're only going to join the deltas in every time. And what the derivative gives us is this delta that we pass on to the next iteration at each step. So how do we get these derivatives? Well, as PL people, we like to design languages that solve our problems, so let's do that. So we're going to define a language where we can express monotone computations. So computations can refer to inputs. For any lattice, we can talk about like the bottom or the least element of the lattice, and we can also join results. We also have different kinds of lattice formers. So for example, we have product lattices. So that's like the set of configurations paired up with the store. We have power sets, which is like the set of configurations. And an interesting thing here that happens is I have this red D. And in order to enforce monotonicity, this element D is not allowed to change as the input changes. That would break monotonicity. So this is kind of like an external computation that can't refer to x. And in the big join, we can bind a variable that refers to these external values, u. Finally, we have a third type of lattice former called maps. So this is like the store in the example. And similarly, the key and the value that you look up in the store, those are also external computations. And so given one of these like ASTs, you can just evaluate it by interpreting the syntax as the actual function. So we can go back to our store widen successor function, and we can sort of implement it in this monotone language. And what that gives us is a bunch of black stuff, that's the lattice stuff, and a bunch of red stuff, which is the external stuff. And the things that we can hope to incrementalize or make efficient is all the black stuff. And there's quite a bit of black here, which means we're going to be able to do a pretty good job of incrementalizing it. So how do we get derivatives? Well, it's just a syntactic transform over the computations. So for inputs, if we take the derivative with respect to x, that's just the change in x. If we take the derivative with respect to x of a different input, y, well, y doesn't refer to x, so it can't change with respect to x. So that's just vacuous. It's empty. Similarly, for all lattices, we get the same thing for the derivative of bottom. The derivative of join just propagates into each side. For products, the derivative also just propagates downwards. For maps, again, since this external computation can't refer to x, it can't change with respect to x, and so the derivative just gets pushed down into only the lattice computations. Finally, for sets, again, these singletons can't refer to x, so they zero out. And big joins are the most complicated case because either E1, the set that we're doing like a for loop over, that can change, and the inner piece, E2, can change. So the derivative ends up giving us 3 big joins, one where we explore the old things that we're looping over under the new change, and then 2 where we're exploring the new change under both the old and the new. So going back to our example, so this is basically like semi-naive evaluation, which you'd find in Datalog. So going back to our example, let's try taking the derivative of it. So our example starts with this big join on the outside that distributes over the set of configurations. So our derivative takes in a change to both the set of configurations and a change to the store. And if we distribute this derivative over the big join, we have these 3 pieces. One where we look at the old configurations and how those change with respect to these store updates. And then 2 for exploring how the new configurations behave. So is this efficient? The answer is yes, because you're not going to explore these old configurations under the old store, and that's what the successor would do. But can we do better? And the answer is, of course, yes. So if we look at this term, what it's doing is it's exploring the old configurations under the store updates. But what happens if there are no updates to the store? Well, we kind of, then we don't expect there to be any change. Additionally, if the store is just a small update that touches a single address, we expect that most of these configurations, since they touch at least 2 addresses, one for the function and one for the argument, we expect that most of them won't actually rely on this change, and so we shouldn't touch them in our loop. So we have one solution for each of these problems. For the first one, we're going to specialize the derivative for a certain kind of change. And the kind of change that we're interested in is what I call the smallest change. These are the join irreducible elements of the lattice. So the smallest elements for a power set are the singletons. The smallest changes for maps are just changes to a single slice. And the smallest changes to a product are the changes in either side. So we can specialize our derivative appropriately based on a small store change or a small configuration change. So for store changes, when the delta configuration set is empty, as in this specialization, what happens is these final two big joins, they zero out because the set that they're looping over is empty. So we're just left with the left big join. And for the other specialization, when the store is empty, what I said before is that the delta inner term zeroes out, and you can see that by partial evaluation. And you can actually compute that. And so that gets rid of the first and the third term, and you're just left with the second term. So in the special case where our changes take this form, we can get these more efficient solutions. Particularly for the second one, it's going to avoid looping over all of the old configurations that we've seen before. Now, do we have to resort to just waiting around defining this kind of change? No, what we can do is we can break down larger changes that we see into these smaller pieces and process them one at a time. And so breaking something down into smaller pieces and processing one at a time, that's just a work set algorithm. So our third fixed point here, which is the efficient one, keeps a scene element, a work set, chooses something out of the work set, and then processes that with the specialized derivatives. And an interesting fact of this is that you can actually choose the order that you process small elements in, which can give you an added efficiency bonus. So the other problem is, what if we do update the store? Then most of these configurations aren't actually going to rely on that change. And so this relationship between the configurations that we're looking at and the change that we're making is really, really sparse. And so what we want is sort of a dependency map from the addresses that we're changing to the configurations that actually use those addresses. And so we can implement that in the fixed point by updating the set that we're joining over here to use that depend function. But to actually compute this, we might be in a little bit of trouble, right? So it turns out that it's pretty easy for this example because we can maintain this dependency map as we explore new configurations. So when you're processing every new configuration, we're going to evaluate this inner term, and when we evaluate it, that's going to tell you the things that it depends on, because we're actually going to look up those addresses in the store. And so this computation, the derivative, which relies on depend, is kind of changing over time because that dependency is changing over time. And so what this maintenance of the dependency thing is really doing is it's capturing how the derivative changes with respect to its input. And so that's the second derivative. So I don't have time to talk about it now, but in the paper it talks about dependencies in general for these monotone computations and the maintenance of the first derivative via the second derivative. And it's important to note that when you implement this, you don't actually compute the second derivative, you only compute the first one. Okay, so in conclusion, how much better did our final fixed point get over our initial one? So it's an average of 60 times speed up, or over the literature one. So it's an average of 60 times speed up. And on the largest benchmark, which was like 3,500 lines, goes from 3 seconds to 70 milliseconds. So for a research object that you code up, 3 seconds is actually not necessarily too bad for a 3,500 line program, especially if you have all the knobs and dials, because it's a research artifact. And that's what we have. But the fact that we still get this huge speed up is very, very nice. And that's including still the knobs and dials. So if you specialize it for our particular case, it would get even faster. The specializations and the dependencies that we use really, really matter. If you just use the normal incremental fixed point, like the semi-naive evaluation, it actually doesn't terminate on some of these examples, on some of the larger ones. And really the reason why this efficient fixed point, the workset one that uses specializations and dependencies, is a lot faster than the adapted set of states approach is because you're going to be able to skip directly from where a change is made to where it's used. So in the set of states approach, if you make a change, you have to step through every intermediate state until you get to where the thing is used. But with the dependencies, you can jump directly from the introduction of the change to where it's used. So if you're interested in looking at the code, it's linked to in the paper. And if you have questions, you can email me or my advisor at these addresses. Thank you.
We have time for a question or two.
Hi, Simon Pate-Jones. I love the way you're defining your transformer and then taking its derivative. I was wondering whether you literally do that. Do you actually have a specialized language in which you write the transformer and actually a computer that takes its derivative and does this stuff? Or is that some stuff you do by hand?
So for my implementation for this paper, I did it by hand. I think interesting future work would be either integrating this with an existing solver or creating my own that actually does this, yeah.
Okay, so if as your analysis got more complicated, taking the derivative by hand might become more tricky?
It's possible, yeah. So in this paper, there was a very limited set of monotone functions, and that was to line up with what we needed to describe the analysis. But in general, you should be able to do this for lots of different monotone things, including like nested fixed points, or DataFun introduces like higher order functions in this kind of language that preserve monotonicity. So I think you can still do this stuff there, yeah.
Cool, thank you.
Hi, I was wondering, when you say that normal incremental fixed point doesn't terminate, does it like time out, or does it get caught in a loop? And is there any like insight into why?
Okay, theoretically, it does terminate, yes. It's practically, it just takes too long, yeah. And that's mainly because you have to reiterate over the set every single time because you're not tracking the dependencies, yeah.
Thanks.